with differential points.
Good afternoon. I'll be telling you about how to privately learn half spaces via privately finding a center point of a set of points. This is a joint work with Shai Moran, Kobi Nissim, and Uri Stemmer. All of them are present in this room. Possible. Oh, yes. Okay. So what am I going to do in this talk? I'll first be speaking about private learning of half spaces. I'll give an overview. Then I'll give define privately learning of a center point, of a point in the convex hull and a center point, which I will properly define. I'll give overview and the algorithm. Then I'll show a reduction from a private learning of half spaces to finding a point in the convex hull. And as a result, we get a private learning algorithm for half spaces taken from a grid x to the d for finite set x with sample complexity which is polynomial in the dimension and very mildly depend on the size of the grid. So it's 2 to the order of log star of the size of the grid. And we will be speaking about the setting without margin, so the dependency on log star of x is essential. So let's start talking about private learning of half spaces. So let's recall very briefly the notion of private learning defined in the Cleaners paper. Again, we have records of people taken from some distribution. Each record is labeled by 0 or 1. We have a learning algorithm that produces a hypothesis. And we want the algorithm to be private. It should be a private learning algorithm. It should, the hypothesis should be good on the distribution, and it should be differential privacy, meaning that if we change 1 point, then the distribution of the hypothesis will be similar, epsilon delta similar. So this is private learning in general. Let's speak about learning half spaces. First, without privacy, we have a set of points in R to the D. We want to find a half space that separates the points. So the half spaces will be all these points on one side of this, in this case the line, but it's in R to the D, so in the hyperplane. So we want the half space to classify correctly all the points. And I'm thinking about classifying correctly the sample, but this implies the pack learning in general. So this is this is learning half spaces. We will want to be able to privately learn half spaces. So in this case, we have a set of label points taken from some grid x to the d for some finite set x. As you can see in the picture, the grid doesn't have to be uniform. The points of the grid can be in different distances, and we have labeled the points from this grid, and the goal is privately find a half space that separates most of the points correctly. And if, what do I mean by private? I mean that if one point moves, its location moves, so the distribution of the output of the algorithm, the half space that the algorithm returns, should have a similar distribution. So again, if we have a private learning for that labels correctly most of the points in the sample, so we have a private pack learning of the entire distribution. We have the generalization given to us. So a few remarks. In this talk, I'll assume that the sample is separable. There's a half space that labels correctly all points. I will discuss it in a few slides, that we can do also the case that it's not separable. Yes?
So is it necessary to assume x to the d, or can you have different sets, like product space with x1?
It can be any product, but it won't matter. You can take always the union of the sets to be the grid. So it doesn't matter. Since we depend on log star, the size of the domain, it doesn't matter. And actually, we can think about not taken from a grid, by taken from some set of points. So it's without loss of generality. So Unlike the previous talk, we assume there's no margin. The points can be as close as possible to the hyperplane. We protect both the data and the label, so we can, if a point moves in the grid, with or without changing its label, so we still have to have the output distribution to be similar. And the last remark that we studied the sample complexity of this problem. Scientifically, our algorithm will have an efficient sample complexity, but the runtime won't be efficient. For some cases it will be, and I'll discuss it when it's in a few slides. So what is known for previous results? So without privacy, we know that this problem can be learned with the sample of size order of 1 point. With epsilon privacy, the exponential mechanism uses sample complexity order of d squared log x. I'm saying it now, and in this talk I will ignore all Greek letters. I will ignore the learning and the learning parameters and the Greek and the privacy parameters. All of them behave as you expect, as you all expect them to do.
Quick question. Did you mean the O of D, the ones that
Yeah.
dimension D?
Well,
Without privacy.
Without privacy.
it's all of, yes. That's 1 equal D. Yes. That's my thought of making changes after my quarters through the slides. So, yes. So epsilon privacy, we can do it with order of d squared log x, and by a work of Vitali and David Shaw, this is there's a matching law bound, so d squared log x are necessary and sufficient to learn half spaces with epsilon privacy. The exponential mechanism in general is not efficient. If we want to have efficient algorithms, so we can use the statistical query model. So there's this SQM algorithm for half spaces of Donegan and Impala, and we can use it to have a private algorithm with time and sample complexity polynomial in D and log x, where the degree of D is at least 4. And if we have margin, which it was discussed by Mark earlier, so Blum et al. Showed that we can do it with, if there's a margin, we can do it by square root of D over gamma squared, where gamma is the margin. And recent results show that you can do it with sample complexity 1 over gamma squared without dependency on the dimensions.
Sorry, quick question. So why d squared was the exponential mechanism? Why not just d log x?
Because the point is d-dimensional, so the number of possible...
Right, but the continent is like x to the d most.
No, it's x to the d squared, because
I see.
because the point is size d. I made this mistake a few times, and I always return to yes. So this was for general D. What is known for the simple case of D equals 1. So for epsilon privacy, we still have the same log x upper and lower bound. For epsilon delta privacy, we can do it much more efficiently. We can do it in sample complexity 2 to the power of log star of x. So it has a very mild dependency on the size of the grid. This was first done by Kobe, Uri, and myself. And another algorithm was given by Ban et al. And the lower bound of omega of log star of x by first for Ban et al. For the proper case, and then Ban in his mark gave another proof in his PhD thesis. And very recently, Alon et al. Generalized this lower bound for also for improper learning of half spaces of a threshold function. Shai will discuss this in his talk tomorrow. So this shows that some dependency on the size of the grid is essential. especially this, in particular, this implies that learning threshold and half spaces over the wheels is not possible. You cannot learn threshold or half spaces over infinite domain. It has the size of the sample has to be depend on the size of the grid. And another important thing is the result of Beimel et al. That proves that under differential privacy, proper fast learning of threshold is equivalent to finding an interior point of a set of points. So this motivates our results. So let's discuss what is finding an interior point. Again, we have a set of points taken from some finite grid, and we have to find a point between the minimum and the maximum point. So this is finding the interior point. And at the warm-up, we'll show how we apply the exponential mechanism to this problem. So the exponential mechanism chooses a point x from the grid, which probability e to the power epsilon times the q of x over c. The q of x is some quality function, and c is simply a constant to make the sum of the probabilities be 1. So this is the exponential mechanism, and to apply this, we need to know what is the quality function. So the quality function, in this case, is the closeness to the median. In other words, it's the minimum number of sample points that we need to remove such that x is not in the interior point. For example, in this case, if we remove these 3 points, the red point won't be in the interior point of the remaining points, so the quality is 3. If we would have taken a point in this segment, the quality would be 4. So this is the quality function that we can define. And what is important is that the sensitivity of this function is 1. If we move one point from one location to a different location, the closeness to the median will change by its most 1. It can increase or decrease by its most 1. So this is sensitivity 1. That's why we can choose work as an exponential mechanism with epsilon q of x over c. And the sample complexity of this simple algorithm is the order of log x, the number of possible candidates that the algorithm can return. Questions? Okay, so let's continue. So this, as I said, there's an epsilon delta algorithm for this point with sample complexity much more efficient. So what is our results in half spaces? We show an epsilon delta pivot algorithm for learning half spaces where the sample complexity is order of d to the power of 4.5 times 2 to the power of log star of x. So for constant d, this has basically the same sample complexity as the algorithm, the previous algorithm for d equals 1. For big D, the dependency of D in this algorithm is worse than the exponential mechanism, but the dependency of the size of the grid is much better.
So,
Yes.
so what is the sample complexity of the SQ learning?
The SQ learning will be worse than that, probably. But the SQ learning is efficient, our algorithm is not efficient, so we have to compare it to the exponential mechanism, which unfortunately we cannot match the dependency on D, but at least for constant D, which is already D equals 2, D equals 3 or 5, is already new, and we give much better sample complexity. So again, D is a dimension, and the samples are taken from the grid x to the d. Up to now, I spoke about the realizable case by a result of Kobe, Uri, and myself from SODA 15. If we have a private algorithm for learning in the realizable case, we have a learning algorithm for diagnostic case with the same sample complexity. So when we don't care about the running time of the algorithm, agnostic and realizable learning, private learning are equivalent. So the same result, our algorithm works also for the agnostic case with the same sample complexity. And if we consider a constant d, and not a general grid, but the grid 1 to the t to the d, the random time of our algorithm will be polynomial in log of t. So this is for constant d and a nice grid, our algorithm running time is efficient. So this ends the part of the overview about private learning. Let's move to the second part, private learning point in the half space, private learning point in the convex hull. So what is the problem? We have a set of points in x to the d, a set of points inside the grid x to the d, and the task is to find a point inside the convex hull of the points. And the point, so for example, we can choose the red point. And the point may or may not be in x to the d. So the output of the algorithm doesn't need to be in the grid. And actually, algorithms that we'll present will not return a point in the grid. And we want this algorithm to be private. What does it mean that it will be private? If we move some point, and this changes the convex hull, the distribution of the points that we choose should be similar. It should be epsilon delta similar. So we want an algorithm that changing the location of one point doesn't change much the output of the algorithm. So this problem wasn't considered previously, so I cannot tell you in the private setting it wasn't considered previously. In the non-private setting, you can simply return some point from the input. So I cannot tell you about previous algorithm, but I think the first thing that I would try is to apply the exponential mechanism. So again, the exponential mechanism will choose a point x with probability e to the power of epsilon q of x over c. And we have to ask ourselves, what is the quality function? And we need some function with a small sensitivity. And a problem that we'll see that will happen, what are the candidates for the point x? So to define the quality function, I have to define the Tukey def of a set of points. So the Tukey def of points was defined by Tukey in 75. The input is a set of points in R to the d. And the Tukey def of a point x in R to the d is the minimum number of points from S that we need to remove such that x will not be in the convex hull of the remaining points. So this is similar to the way that they define the quality function for d equals 1. For example, if I take this red point, how many points do I have to remove that the point won't be in the convex hull? 3. I also thought it's 4 and found. So if I remove all the points to the right of the line, the red point won't be in the convex hull of the remaining points. One comment, so this notion is used in geometry, and they usually define it, they have a more geometric definition, but for us, this is the correct way to define it and understand why we use the Tukey def. So, for instance, if we take all the points outside the convex hull, all of them have Tukey def 0. All the points in the convex hull have Tukey def greater than 1, at least 1. So if you want to return a point in the convex hull, it's enough to return a point with Tukey def greater than 1. And for in this case, if all the points in the red polygon have Tukey def at least 2. So it's a polygon which has strange nodes, but these are the points of depth 2. So this is a Tukey def of in this case. And the Tukey-Def, there's a very nice property that we'll use. So for every set S in R to the D, there's a point X in R to the D such whose Tukey-Def is at least S divided by D plus 1. So let's see that this is reasonable. If it takes D equals 2, D equals 1, there's a median. That's what it said, but it's just generalized to every dimension. One problem that we'll have, that the point is guaranteed is not one pointer in the sample, but it will be some point in R to the D. So for instance, if we take this red point, we have 9 points in R to the 2, so its Tukey-Def is at least 3. In this case, it's 4. So we are guaranteed that we'll have a point with the Tukey-Def 3, and it has a Tukey-Def 4. And two definitions: the Tukey median of a set of points is the point X in R to the D with maximum Tukey-Def among all the points in R to the D. And the center point is a point X in R to the D whose Tukey-Def is at least S over D plus 1. So rephrasing the terms that are mentioned, every set of S in R to the D has a certain point. So finally, you can understand the title of this talk.
Can I ask?
Yeah.
Is X a member of S?
No. If the points are on a circle, for instance, you have to take a point in the middle. So as I said, this will cause us problems that we'll have to deal with when we design the algorithms. So going back to the exponential mechanism, we know what the quality of a function. The quality function that we will use is the Tukey-Def. And this function has sensitivity 1. If we move one point from one location to another, the number of points that we will need to remove can increase or decrease by 1. So this is a nice function. As I said, there's a problem that we know that there's a point with high Tukey-Def. It's not in the. It's not even if it's not in the sample. Even if you take a point from the grid, it's not necessarily in the grid. So we have to have a small set of candidates to have the exponential mechanism. I know I won't go into detail, but thankfully the geometry helps us, and it says that there's a small set of size x to the d third, d cubed, such that all the Tukey centers lines for all points of the grid, for all sets that are contained in the grid, are contained in this set T. So there's a small set that we can take as candidates. If we apply the exponential mechanism, the complexity will be d cubed times log x, where the d to the 4, not d cubed, where d cubed comes from the size of the set, and another factor of d comes from the fact that the Tukey-Def is only s over d. So we lose another factor of d because the quality is only s over d.
Is it clear why it should be x to the d cubed for the size of the set?
It has to be at least x d squared, but this is the best. What we know, I'm not expert in geometry, and I'm not clear if it might be. I think it's true, but I'm not. If you can show me better, I will be happy, but sure. I'm not sure.
Either way, this isn't like an obvious statement, okay.
Well, what you mean clear that we need to have this? This is what we know how to prove, and later we'll be dependent on the log star of this, so we didn't bother to optimize this. So this is okay. So as Gautam said, the way we know how to implement the exponential mechanism, this is the best what we know. Maybe with a little bit more of geometry, we can improve it slightly, but not too much. So what are our results? We show an epsilon delta private algorithm for that set, for every set S, where the site of S is big enough, we find a point with a point whose Tukey depth is at least S divided by 2D plus 1. So if we wouldn't have this factor D, it would be a center point. So this is the approximate center point. And the complexity of the size of the set S, the sample complexity of the problem, is D to the power of 2.5 times 2 to the log star of X. So we'll have the complexity that we want, that we can achieve dependently on the size of the domain, and it will be D to the power of 2.5. In particular, this private algorithm returns a point in the convex hull. And we prove lower bounds. Every algorithm, private algorithm for this problem, for every epsilon delta private algorithm for finding a point in the convex hull, its size of the S has to be omega of D plus log star of X. The D is new, and the log star follows from the lower bound for threshold, for the interior point. And if we only care about, if we would want epsilon differential privacy, so the lower bound is bigger, D squared log X.
Sorry, why D is new? Is it like, doesn't it follow from the non-private center complexity?
It's finding a point in the convex.
This is for the
Convex hull, yes.
Sure.
For the, again, this is an example of a problem that in the non-private case, you can return a point from the sample. It's enough that the size of the sample will be 1. But in this case, we have to work a little bit to prove the law, but it's not.
Sure.
So let's go into the details of our algorithm. So algorithm has to find a point, a d-dimensional point with high Tukey depth. So we'll find the point coordinate of the coordinate. And we'll first of all explain how to find the first coordinate, and the other coordinate will be found similarly. So we define a quality function Q from R to N. Its input is the first coordinate of the Tukey depth of the point, and the quality function is of y is the Tukey depth of the best extension of y to a point in R to the d. So we take the maximum over all points y2 to yd, the Tukey depth with y, and the extension. So the best extension possible for the point y. And what do we know? We know that the center point. We know that's a point with Tukey depth at least s over d plus 1. And if we take its first coordinate, the quality of this point of y will be s over d plus 1. And what we find, and I'll say something about how we do it, we find a point x1 whose quality is not as promised, but we add some deterioration, s over 2 times d plus 1 squared. So we lose something in the quality of the function, of the point we find. By differential privacy, we have to lose something.
Is this related to the one-dimensional two thresholds?
Yes. I'll explain how. Wait 2 slides. Okay. So, and in general, we do in the d-dimensional for all coordinates, we want to find the point x1 to xt. So for each I equals 1 to the d, we define a quality function which is the same as the previous quality function, but in this case we'll have the first I minus 1 the coordinates that we already found. This is the one y that we want to find the quality of, define the quality of, and we look at the best extension to point R to the d. So this is quality function q of I with respect to the previous points that we coordinates that we already found. By induction, we'll have a point which is what is guaranteed by the two-key def minus I minus 1 times this something that we lose. And we know that there's such a point, and we will lose another factor of s over 2d plus 1. So in each step, we lose this quantity. After these steps, we found a point x1 to xd whose quality is a two-key def of x1 to xd. We don't have the maximum anymore. And if we sum out what we lost at most half of this quantity. So we're left with the point where the def is at least s times s divided by 2d plus 1. So this is algorithm. What I didn't tell you how we find this point, each coordinate. So how do we define a coordinate? I'll say how we find x1, but it's only to simplify the indices. So again, we have the quality function, and to find our goal is to privately find x1 such that q1 of x1 is high. And what we do is we use the algorithm, our algorithm from 2013, Concave, that finds x1 with good quality. So this is the algorithm that we use to solve the threshold. So we use the same algorithm, but in this case we use the coordinate of the coordinate, I think this Concave algorithm is a very interesting tool that has been used by us for the threshold and by Uri and Kobe for clustering, and I think it has many more applications and people are not aware of, so let's explain the property of this algorithm. The theorem that we proved, if we have a function, I'm writing specifically the quality function depends on the sample and on the x, which is the point in R. It had to be some quasi-concave, which I'll define in the next slide. It had to have sensitivity 1, and the size of the sample must be at least to the power of log star x. This is where we lose this factor of 2 to the power of log star x. If we have such a function, then Concave on input s find a value x such that q of sx is close to the maximal possible value. And closeness will the exact sample complexity will depend on the amount of closeness that we require. So what is a quasi-concave function? So we call that the function is concave if we have a, b, and c. So the value of f of b has to be above the line connecting a and b. This is a concave function. A quasi-concave function can be much uglier creature. And what we require that if we have a, b, and c, the value of f of b has to be bigger than the minimum of these 2 points, the Fourier function. So this has to be bigger than the minimum. In other words, the function has to be non-decreasing in the first part and non-increasing in the other part. It can have plateaus, but it cannot have a local minima besides it cannot have local minima. Yes?
Is this synonymous with unimodal or not?
So since I don't know the definition, so...
I guess it goes up and then it goes down.
So we can have plateaus. It can stay the same. And actually, when we applied it for the learning, the values were the error, so it would stay. It had plateaus, so it doesn't have to. It's decreasing and then non-decreasing, but it can be like this. Like this, like this.
In one dimension.
It's a one yes. This algorithm works for one-dimensional functions, and what we managed to do that when we do it coordinate after coordinate is to learn something, is to find, to optimize the D-dimensional function. So let's see a simple example. Uri, how am I with the time?
We started like 10 minutes at least late, so
So when did it start?
I guess 20 more minutes or something.
So, okay, so I'm good on the time. So what I want to show an example of a quasi-concave function is a Toki def for the case d equals 1. So we have a point A, in this case its Toki depth is 4. If we remove this point, it won't be the it won't be in the interior point, and we have 2 points B and C. So the Toki depth of B is greater than the Toki depth of C, because if we have to remove this point in particular to make the B not in the interior point. We have to remove the point of C. And if the Toki depth of A would have been less than C, we would have the symmetric argument. So for D equals 1, it's easy to see that the Toki depth, the closeness of the median, is a quasi-concave function. And this is how we can apply our algorithm to find a point in the interior point, which is equivalent to learning threshold functions. So, as I said, if we want to find x1, we use the recurrent algorithm to apply that. We have two challenges that we have to deal with. We have to prove that the function q1 or qi that we defined is quasi-concave. We have to use some geometry to prove that. And we need to discretize the domain. As I said, we know that there's a point in R that is a center point and not on a grid, so we had to use the same results that I showed before, or generalization of that, showing that we can choose x1 from a small, fairly small discrete domain. So this is the idea of finding a point in a center point. So conclusion, we have an epsilon delta algorithm that works for set size of size polynomial in D and 2 to the log star of x, and finds a point with a large Toki depth to approximate center point, s over 2 times d plus 1. So this is what we know about the convex hull. And this ends the second part of my talk, and so let's go to the third part of my talk. We want to learn half spaces by showing a privacy preserving reduction from learning half spaces to finding a point in the convex hull. So we have a private algorithm for finding a point in the convex hull. We use it as a black box. We will have a reduction which takes a set of labeled examples and construct a set of points, feeds this into the algorithm. This algorithm returns the point, and we will understand this point as a half space that we return. So again, if Barnett al showed a reduction for the case d equals 1. This reduction doesn't work for, at least we don't know how to make it work for d bigger than 1. So we show a different reduction, which is more complex. So how does our reduction work? We use the sample and aggregate approach. So we take L large enough samples, subsamples, and for each one, non-privately, we find a consistent half space for this subsample. So after the step 2, we have L half spaces for each subsample. And now we have to privately combine them into one hypothesis, into one half space. So we take a convex hull, a point in the convex hull of these half spaces. So we look at the half space as a d plus 1 point in D, r to the d plus 1, and we have L points in r to the d plus 1, and we find the point in the convex hull, and this is the hypothesis that we return. So I'll explain in 2 slides why this is good.
So one question here. In particular, suppose you could just privately release any of them would be good, right?
No, this hypothesis, we used a non-private algorithm to...
Right. I understand that they're non-private, but if, say, somehow magically they would all have the accuracy guarantee you want, any single one of them, right?
Every one of them will have the accuracy that we want. Actually, we'll need them to have a much better accuracy than we need.
Okay.
But non-privately, yes.
Yeah.
We can return all of them with the problem that we need to return something with privacy. So first thing that we need is the fact of the sample and aggregate. If we take subsamples and we change one point, so for instance, we have this point here that moved from year to year, so only one hypothesis will change. So every sample, every neighboring samples will change one hypothesis. This means that that it's enough to construct a private algorithm whose input is L half spaces. If we'll protect the privacy of these L half spaces, we'll protect the privacy of the original sample. So this is what is usually done in the sample and aggregate. So this is good. We have to combine H1 to HL in a private manner. So why is it sufficient to take a point in the convex hull? So let's start with having two half spaces. So finally, towards the end of my talk, I'll give the formal definition of a half space. So half space is determined by deep values A1 to AD and a W, and the hypothesis gives 1 if and only if the sum AI xi is bigger than W. So this is H1, and we have another hypothesis with A1 prime to AD prime and W prime. So again, it returns 1 if the sum is bigger than W prime. And now we'll take the average of this two half spaces. So we take the 0.5 A1 and 0.5 A1 prime and so on. And we multiply that by x1, and we take the average of the weights, W. So this is the average of two hypotheses. And if we have two half spaces that give the same value A, then the average gives the same value to this point. Meaning that if these two values give the correct value according to the target function to the point x, so the average also gives the correct value to the point x. And this is there's nothing special about average. We can take any combination, convex combination of these hypotheses, and we can do it for many hypotheses. So if HL1 to HL are all correct on the point x, then every convex combination of this hypothesis is correct on x. In other words, if we take a convex combination, the error of the resulting hypothesis will be the sum of the errors of each hypothesis. So if we take all of them to have small error, so the resulting H will have a small error, and this is a generalization error. So this is a reduction. As I said, in this case, we know to prove that the error will grow the sum of these errors. We have a better analysis if we not just a convex combination. If you take a point with high Tukey depth, then the error will be less than the sum. And using this reduction or the improved analysis, we get the algorithm of learning in the complexity of d to the power of 4.5 times the log of the 2 to the log star size of the domain. So conclusions, we show how to privately find a point in the convex hull which height Tukey depth. The sample complexity will be poly d times 2 to the log star of x. We prove a low bound on the sample complexity of this task, and we use this to privately learn half spaces with the same sample complexity. As I said, we have a poly d times 2 to the log star. We have similar low bounds. The open problem is to improve the dependency on d. So the low bound is, for this case, is d plus log star. Can we improve it from d to the 2.5 to d? And if we will remove it, improve the finding this complexity of this problem, we will improve the complexity of our learning algorithm. That's all. Questions?
No questions? Thank Amos again.
Sorry, I can ask.